Hello again. Welcome back to Luxi, a podcast to reignite your wonder by exploring the science behind luxury items. I'm Dr. Lex, PhD, infectious disease expert, and jewelry lover. I'm joined by my co-host Dimos, also a PhD, electrical engineer, and material science enthusiast. So we're continuing our theme of materials used in fine jewelry with platinum. I think the first time I saw platinum was with my grandmother's wedding ring set. It wasn't super fancy, but it was made out of platinum, and I noticed how different it looked than silver, and we'll get into some of the reasons behind that in a minute. But Dimos, what's your experience with platinum?
I don't have any real experiences outside of thinking that, maybe, I guess I always thought it was something expensive, but I never really understood it until I started researching it for this episode.
Cool.
Yeah.
So here's a microbiologist and electrical engineer's take on the science of platinum. A bit of background first. Dimos, do you know the atomic symbol for platinum?
I think it's PT.
Yes, and its atomic number?
I do not. I did not check that.
It's 78. Do you remember what silver was?
47.
Yeah. So platinum is dense, malleable, ductile. Do you know what ductile means?
You can pull it into a wire.
Yes. And highly unreactive. Not just unreactive, highly unreactive. And it's one of the least reactive metals that we know of. It's a silverish white transition metal. Do you remember what a transition metal is?
It's a metal that is in a special place on the periodic table.
It is, and it has that ability to make a cation in a d electron shell. So the name originates from Spanish platina, which is a diminutive of plata, or silver. It has 6 naturally occurring isotopes. Do you remember what an isotope is?
Yes, an isotope is a stable or unstable version of an element where you have excess neutrons, or just the right amount.
Yeah. So same number of protons, so same atomic number, but different number of neutrons. It is a rare earth element, an average abundance of about 5 micrograms per kilogram, and only a few hundred tons produced a year.
Yeah.
Do you know where the majority of platinum currently comes from?
Is it South America?
South Africa.
Oh, South Africa.
Accounts for 80% of the world production of platinum, found usually in nickel and copper ores, but sometimes on its own because it is so unreactive. So archaeologists have found platinum in gold used in ancient Egyptian burials, although they think it was an accidental contamination as opposed to the Egyptians consciously using the platinum. Pre-Columbian Americans in Ecuador used platinum white gold alloys to produce artifacts. And the tradition of platinum working is usually traced to South America in the La Tolita culture from 600 BC to AD 200, but precise dates and locations are hard to pinpoint. They would combine gold and platinum, and the resulting alloy would be soft enough to shape into tools. The first European reference to platinum is in the 1555 writings by an Italian humorist describing an unknown noble metal found between Darien and Mexico. In the 1700s, there was a more scientific study of platinum by various chemists who presented their findings in paper describing the metal. And in 1786, Charles III of Spain provided a library and laboratory to Pierre-François Charbonneau to research platinum. Charbonneau succeeded in producing 23 kilograms of pure malleable platinum and started a business, ushering in the so-called Platinum Age in Spain. Platinum has a variety of uses, and can you guess one of them? We already know because it's why there's some really noisy Priuses in our neighborhood.
Oh yeah, platinum is used as a catalyst, which is a big part of what I'm going to be talking about.
Well,
too.
Specifically in catalytic converters. Not sure if that's why they keep getting swiped out of the Priuses, but...
yeah, there's a lot of expense making a catalytic converter.
Yeah. Laboratory equipment, electrical contacts and electrodes, and, of course, in jewelry, but also, interestingly, in dentistry equipment. Platinum is also used in the glass industry to manipulate molten glass.
Very high melting point.
So platinum's popularity in jewelry is due both to its strength and durability, but also to its prestige, since it's rather rare. And even though it's very strong and very durable, it does get scratched and dull, so it requires cleaning and polishing every few years, which explains why my grandmother's platinum rings looked like such a different color than white gold or silver, because they needed a good polish, I think.
Yeah.
It had been a few years. Okay, so what did you find out about platinum?
There was a lot of interesting information about South Africa and South America. It was kind of called a white gold. And I love how there was this description saying that it was both resistant to fire and incapable of destruction by any of the Spanish arts.
Okay,
So,
what are the Spanish arts? Is that
well, I think
was it impervious to the Inquisition?
I guess you could use it to make a paella, but you couldn't like melt it out. Well, I think the issue was that a variety of gold processing techniques already taken up by the Spaniards, and given their colonialism, they had also brought in an enormous amount of gold from those colonies. Were processing that in Spain. They were
Although I do
quite
think
good.
it's interesting that the native cultures of South America were quite adept at metallurgy in their own right, and likely taught the Spaniards a thing or two, and that's just been lost to colonial history.
But what I enjoyed was the book that I read on it definitely gave credit to those early cultures. At some point, it was written down, or at least it was acknowledged in history, that these Ecuadorians. But even though recent archaeological digs have also been part of.
Yeah, I think it's probably
part of
more
the
likely.
I imagine the conquistadors were probably like,
No.
"Oh, look what we found."
They really weren't. They weren't big on citing the work of others.
The natives of Ecuador, from what I had learned, were capable of quite complex metallurgical industry. They had actually been able to purify platinum to the point where only 4% of the platinum had impurities in it.
It's impressive.
Yeah, and they were able to make quite a bit of jewelry. Enough platinum was able to come back to Europe from the colonies that scientists were able to actually start doing research then.
Yeah.
And it was just a strange and difficult to use material as far as Europeans were concerned. Interestingly, there is this talk of the 6 old metals: copper, tin, lead, iron, gold, and silver. And this was called the new 7th metal. Even though obviously we're not talking about any knowledge of the periodic table at this point. But kind of a very early, very rudimentary understanding of metals at that point. Willem Siemens, who is very well known in Europe because it's like the #1 appliance manufacturer. He was kind of Europe's Thomas Edison. Was one of his first major advances in science, and it could be very well said it was almost as important as the light bulb, was creating a thermometer out of platinum. But
So not mercury.
No. Go ahead and
No.
tell me what you're looking for.
No, I was gonna, inject a intelligent quip, but the moment has passed.
Oh, sorry. Well, I see you pulled up a periodic table, and that's always
Whoa,
good.
it's some reading over the shoulder nosiness on the podcast here.
Yes. Well, I mean, I can see your computer right there. In any case, one of the things that this thermometer did was it was capable of measuring an extreme amount of temperature range, from ultra cold as you could get in the 18th century, to as much heat as you could generate in the 18th century, even to the point of, like you had mentioned earlier, using platinum for manipulating glass.
So, question. Do you happen to know if this thermometer was on the Celsius or Kelvin scale?
Well, these measurements were still kind of early on. I mean, don't forget, there's also Rankine. So there is a third scale.
I thought Rankine was for radioactivity.
No. That's Röntgen.
Oh, okay.
But Rankine is an English scientist, had another temperature scale. In fact, to this day we use Rankine for rocket engines. But in any case, one of the things that we found out, though, as more and more scientists came together to understand this amazing device, this thermometer, which helped to make science more accurate and more doable.
Wait, was it the first? It couldn't have been the first thermometer.
It wasn't the first thermometer, but what was important about the Siemens thermometer, and remember thermometers have been around for quite a long time. Maybe we should do a podcast about them.
Thermometers.
Yeah, seriously. But this one, it wasn't really truly accurate until 1885. So these were electronic thermometers of the best of the day, electrical thermometers. It was only until 1885 that it was improved to the point that it was completely accurate from negative 285 degrees Celsius, and yes, they were able to do this in 1885, all the way up to 2000 degrees Celsius. The same thermometer could be used, the same little platinum wire could be used to measure all of those temperatures. Cool. And do it accurately. So by 1937, this thermometer, and I'm just going to stick with this thermometer because I just love this thermometer. This thermometer was used to even make steel of excellent quality and repeatability. Up until that time, there's no way to measure the temperature of steel alloys. And when you're making an alloy, There's a guess. There's educated guesses at how good the quality of your alloy is, but there's no accurate way to create a quality alloy unless you can measure its temperature.
So what does the temperature tell you about the alloy?
It actually will tell you if it's a binary or a ternary alloy, what exact concentration of metals are in the steel, because the steel will become liquid at a specific temperature based on an alloy concentration.
Gotcha. Well, that's very interesting. And then you would want, so what type of alloy makes the strongest steel?
Well, there are carbon steels.
Well, I mean,
there's chrome, there's vanadium.
At the time you're talking about.
I think carbon would probably have been the most common, carbon steel. Because if you adjust the level of carbon mixed in with the steel, you can change the steel's ductility and malleability. What I'm thinking is, one of the reasons the Titanic sunk was when it hit the iceberg, much of the steel in the bulkheads shredded or shattered and didn't actually bend.
Oh, like concave or anything like that.
Yeah. And so instead of there being a dent in the ship, there was a gash in the ship, which allowed an enormous amount of water to flow in. If the alloys were able to be made predictably, that Titanic may have still been floating today, because those steels would have been made to be less brittle and potentially more ductile.
I think that's probably one in the veritable cornucopia of errors that happened.
There were many errors.
Yes, there were many errors that night, unfortunately.
Plus that unhealthy Hope Diamond.
I mean, it was
haunted.
Cursed. I think.
Cursed. Thomas Edison, interestingly enough, used platinum as one of his 10,000 filaments as he was searching for the perfect light bulb filament.
I mean, he or, the 10 underpaid grad students he had working for him. One of the two.
It would take a long time to go through 10,000 things. I mean, he used horsehair, camel hair, bamboo rods. He carbonized everything. He couldn't carbonize platinum, but he was amazed by platinum because platinum had such a high melting point. Would have been an ideal way. But of course he was cheap, so he didn't go and buy it from like a scientific supply store. He took some old batteries, whacked them with an axe, and melted them down and purified the platinum out of them.
That sounds super safe, by the way.
This is how you used to get things, I guess, back in the day.
I don't know. I feel like it's the way you still get things.
I do whack a lot of things with axes. It's true. This is the time of year too, the axe time of year for me. I just whacked a chandelier actually this morning. Unfortunately, upon reaching incandescence, the platinum wire turned the bulb black.
Oh, that's not helpful.
No, but what it was is the bulb was coated on the inside by platinum gas. So he pulled a vacuum.
Yeah. I guess you don't think that like something like platinum would make a gas, but theoretically, I guess anything can make a gas.
It sure can.
It's a matter of temperature and pressure.
Remember this platinum? So Thomas Edison got super excited. Platinum got white hot.
Yes.
Turned into the most awesome light bulb he ever made.
And then
I can see him jumping around the lab saying, "I finally got it.
And then
finally got
darkness.
That bulb." And then darkness. It just got darker and darker and darker until it turned black. Here is where science meets good luck and ignorance.
Oh, no, it's not ignorance. It's a Pasteur's line. Chance favors the prepared mind.
Okay. Thomas Edison said, I got to figure out a way to stop this. I just want some light.
Yeah.
He took another bulb and put a little plate in the bulb. Maybe the platinum will be attracted to a metal plate and not to my glass, and it'll keep on shining. And I'll be done with this terrible experiment. So he turns on the bulb. Nothing happens to the plate. So he starts playing some games. He attaches a battery to the plate. Maybe I can suck the platinum there with a charge on the battery.
Nah, probably not.
Guess what? He turned the battery around. He tried it one more way with the battery flipped around backwards, and it worked. It was awesome. But the battery would run out of juice.
Well, yeah. It's flipped around backwards. And
Yes, but the battery wasn't connected to anything. It wasn't connected to anything. The battery was only connected by one wire. To drain a battery, you have to connect two wires.
Apparently not.
There was a invisible wire connected inside the light bulb. Thomas Edison unwittingly developed the first ever vacuum tube that we today can thank for anything
everything
electronic, including the computers we're reading on right now. He called it the Edison effect, filed it away, never to be studied again by him.
Mm-hmm.
It took other scientists
Yeah.
who sort of unearthed this discussion about the Edison effect and said, hey, Thomas just completely dropped this little banana peel on the floor for him to slip on and for the rest of us to watch and laugh. And now we are going to take this all the way. And Lee DeForest took that same Edison effect that was discovered thanks to platinum
Mm-hmm.
to create the first vacuum tubes.
Cool.
So there. Oh.
I told you, chance favors the prepared mind.
Oh, yeah. And boy, is there more. Now I can go into catalyzing, too. I don't know if it'll get boring or anything, but
I think you've got probably maybe one more anecdote.
And one more
we
anecdote?
Should probably
Gosh,
switch
okay.
just for the length of the podcast.
I love talking. The oxidation of ammonia to create nitric acid was another really great thing that would be done immediately using platinum. And we're just talking about making a platinum foil, or platinum wool.
Mm-hmm.
You can pass the ammonium over that with a little bit of heat and create nitric acid. This is the basis for explosives and fertilizer. Originally, Chilean saltpeter was being used for that purpose. But there was an enormous need with the onset of various wars, including what would eventually be World War I, to do this in an industrial method. And it led to an enormous growth of an industry of building stuff using platinum.
Cool.
I've got a few other quips, but we can throw those on the website. But I will throw in the final quip.
Okay.
And that is this.
All right.
The final use of platinum, which I've been dealing with lately, is building fuel cells for some upcoming missions to our favorite satellite, the moon. Fuel cells to this day use, among other things, platinum as the reactant that allows hydrogen gas and oxygen gas to come together. And it's the platinum electrodes that allow that to form water and lots of electricity.
There you go. Cool. Modern application for an old technology. I obviously have something a little bit different.
Oh, yeah. Talk to me.
I'm going to talk about the anti-tumor properties of platinum.
No way.
Yes. Do you know the definition of a chemotherapeutic?
Hey, something that uses chemistry to help you?
Chemical entities used to treat or cure cancer.
Okay.
This researcher, Rosenberg, and his team discovered the anti-tumor properties of platinum, or they were at least the first ones to publish it, in a paper entitled Platinum Compounds, a new class of potent anti-tumor agents, and that was published in Nature Cell Bio in 1969. The team subsequently published in the journal Naturwissenschaften, I'm sure I said it wrong.
Say what?
Naturwissenschaften.
Okay.
In 1973.
Sounds German.
I'm sure it is. It was just very fun to say.
Mm-hmm.
So I'm going to dip into my well of review articles to start off this discussion. Giuliano Ciamrimboli published a great review of platinum chemotherapeutics in the journal Biomolecules in 2021, and that's where we'll start. So cisplatin was the first platinum drug approved by the FDA in 1978 for the treatment of testicular cancer, advanced ovarian cancer, and bladder cancer. It's still used in combination therapy for solid tumors, so bladder, cervical, ovarian, lung, gastric, breast, and head and neck cancers. And it was considered almost curative for testicular cancer when it was first approved. So nearly half of all chemotherapeutic protocols for cancer contain platinum derivatives. Yeah, it might explain why chemotherapy is so expensive, too.
Yeah, that's true.
I mean, not all of it, but... So, mechanisms of action. How does this work? The platinum binds to the DNA of the cancer cells, much like silver can bind to bacterial DNA from our last episode, and produces distortions of the double helix. This impacts DNA transcription and replication and induces our favorite cell...
Apoptosis.
Apoptosis. That was how I would learn to say it. There are varying pronunciations for that word.
Okay, well.
I like apoptosis. It just because it has that pop in it. Because the cells pop open.
Oh, it's the apoptosis.
Cancer cells, by definition, cannot properly repair DNA, and so they are more sensitive to the effects of platinum. So they will die first before your regular cells, and that's the whole idea, usually with cancer chemotherapies, right?
But this chemotherapy affects every cell.
It does. I'm going to get into some of the side effects.
Yeah.
So platinum also binds to other cellular components and modulates the activity of the immune system. In a review article by Cedric Reeb et al., they discussed something called immunogenic cancer cell death, or ICD. This is when the cancer cell changes the composition of the cell surface and releases molecules, and this happens in a defined sequence, then activate receptors expressed by dendritic cells, and dendritic cells are those immune cells that are running around gobbling up bits of stuff and put it on their surface so that they're like the body's warning system. Hey, look, something's wrong, big flashy red light. And then the dendritic cells stimulate T cells by presenting tumor antigens. So essentially the cancer cell makes itself more visible to the immune system. So platinum cancer drugs are particularly good at inducing this ICD effect, and this can lead to the eradication of cancer cells, and oxaliplatin being the best drug for this. So unfortunately, cancers can develop resistance to platinum-based drugs, and the drugs come with some pretty severe side effects, including nephrotoxicity, which is kidney toxicity, ototoxicity, which is development of hearing or balance problems, so it's ear.
Ototoxicity.
No. Opto.
Opto.
Yeah.
Okay.
I know. Myelosuppression, which is reduction in bone marrow activity resulting in fewer red blood cells, white blood cells, and platelets, and peripheral neurotoxicity. The side effects mean that the doses of platinum drugs are limited, so you can only dose so much, present severe quality of life challenges for patients. One paper by Frenzel et al. Published in Biomolecules focused on why people get these side effects from platinum drugs and found that human organic cation transporters play an important role in the side effects, and children who have a mutation in this HOC2CT2 gene are less prone to developing the ototoxicity after therapy with cisplatin. To combat resistance to platinum drugs, researchers are looking for other platinum derivatives and are looking at different delivery strategies. Much like silver, platinum can be developed via nanoparticle to better target just the cancer cells. One group of authors found that nanoporous silica could be used as a nano container to deliver the drug, and then you could target either like an antigen on the tumor cell or something like that. One delivery method I really thought was cool is photoactivation.
Now, in a situation where you have a malignancy and you don't know where your tumors are, then you're really going to go systemic.
Well, no, but see, the thing is, if you have a very specific antibody-antigen pairing, it doesn't matter. The nanotainer can roam around. It'll only bind to the tumor antigen when it finds it.
Oh, wow.
Yeah.
That's neat.
Yeah, so you can be really targeted that way.
Okay.
But one of the ones I thought was really... These are... The photoactivation is more where you know where the tumor is, right? So Zaiwen Day and Xingang Wang published in Molecules in 2020 looking at several different strategies for photoactivation, including photoreduction, photo-uncaging, and photodissociation.
How cool is that?
Yeah, so photoreduction is a chemical reaction under the influence of radiant energy. This is using the spontaneous cellular reduction of the platinum complex to be a photo-induced reduction. So basically you're activating this by radiation.
Oh, wow.
And it reduces in it.
Photons are radiation.
And it unlocks the platinum complex. Yeah. You can also cage a molecule. So you can cage the platinum drug. And then you can only reveal the active region of the platinum drug by photolysis of a shielding molecule. So you have a shielding molecule, and then it requires the appropriate wavelength, intensity, and timing of the light to basically cut that shielding molecule off and then expose the drug.
Well, I can understand beaming radiation into a body so that if you've ingested this treatment, that you could use photons of radiation to do that. But how do you get light into the body to uncage it?
That they weren't specific on. Yeah.
Right.
This is the one that you were talking about, photodissociation, where the chemical compound is broken down by photons. So basically you can have a inert molecular complex of the drug with something else, right?
Okay.
And then when it gets hit by photons, it dissociates, then you get the active moiety of the platinum drug. So basically it's designing the platinum drug so they can only be activated when they're in or near the tumor cells.
Okay.
Which I think is kind of cool.
I mean, it's still pretty wild. I don't think I understand it all, but it's kind of cool that there are these techniques to increase the amount of platinum you could get to the cancer.
Right, and not to the
platinum do its thing.
Yeah, and not to the rest of the body.
Yeah.
I mean, there's a lot of different tumor targeting mechanisms that are in use right now for a lot of different drugs. Of course, because I'm a microbiologist, I have to mention antimicrobials. So platinum-doped silver nanoparticles are being explored as a way to enhance silver ion release and lead to more antimicrobial activity. Mm-hmm. And finally, can't really ignore the environmental impact of platinum.
Okay.
Yeah. So the mining of platinum notwithstanding, which it's mining, so I'm sure there's some level of environmental impact there.
Mm-hmm.
A 2019 article by Yasmina Rinkovec discusses the measurable quantities of platinum, palladium, and rhodium airborne particles due to the metal's use in catalytic converters.
So it's basically just rattling out of those exhaust pipes.
Yeah. The concentration of these metals has increased over the past 20 years, but the health implications are still debated. Not a whole lot of clear evidence about health implications of inhaling particles of things like platinum.
So we're all getting platinum lung.
We might be. So this is just one more thing to worry about with car emissions. But electric cars don't have catalytic converters, correct?
Oh, no. Catalytic converters are for dealing with exhaust gases, which we don't have in electrics.
Telling you, electric cars, way to go.
Mm-hmm.
No peeking on the answers to my glossary questions.
Man. I keep looking over your shoulder and it's driving you crazy.
It really is. Glossary time.
Yeah.
Isotope.
A stable or unstable version of an element regarding the number of neutrons it has.
Yeah. Kind of overcomplicated it. Atoms that have the same number of protons, but different number of neutrons.
Yeah.
Chemotherapeutic.
It would be a cancer treating drug.
Yeah. Photoreduction.
The ability to disconnect or take away a covering from an element.
It's technically a chemical reduction under the influence of radiant energy shift.
Oh, yeah.
So you can use photoreduction for a number of different things. It's not just for targeting cancer cells.
I'll take it.
All right. Do you have any glossary terms for me?
Oh, gosh. No.
Okay. Do you have any fun cocktail party facts for me?
Oh, yeah, sure. Hold on a second. Let me go to my notes. Yes. Did you know that you can keep a ship from rusting by putting a piece of iron, connecting it to a 12-volt battery, attaching one side of the battery to the ship, and the other side to a piece of iron? Now, that iron will rust, but if you coat the electrode with platinum, it won't rust, and it will allow that ship to float through its salt water without rusting.
Is it just rust? Because salt is corrosive in other ways than rust.
Yeah, well, anyway, it's anti-corrosion.
Oh, okay. Sorry. Didn't mean to steal your thunder.
Oh boy, that went over like a lead balloon. Or a platinum balloon, which would be heavier? No, maybe not. I think lead would be heavier.
Yeah, I think lead's heavier. Oh, wait, hold on. Let me pull up my periodic table of elements.
Oh boy, hit me.
Where's lead? Do you know?
PB. It's PB.
Like PB and J.
Is it a transition metal?
Yeah, it's right here. 82. So yes, that would be heavier.
But not by much.
No.
Hey, what's silver?
AG. You're right. It was 47. I stand corrected. 74 is tungsten.
Okay.
But they are
That's
all
heavy.
transition metals. Yeah. Gold is 79.
Well, anyway, this podcast has gone long, but it's chock full of usefulness.
Well, I have my fun cocktail party facts quiz.
Oh, yeah, sure.
What language is the word platinum from?
Spanish.
Where does most of the world's platinum come from?
South Africa.
RSA, the Republic of South Africa.
Oh.
That's all right. South Africa. All right. I hope you enjoyed exploring platinum with me and Dimos, and I hope you remember a little fact from this episode the next time you see platinum, or start a car, or go to the dentist.
Computer.
Use your computer.
Make a call.
Make a call.
Use fertilizer.
There you go. Ubiquitous. Thanks for listening to this episode of Luxi. A very special thank you to my audio engineer and co-host, Dimos. Our theme music is Harlequin Moon by Birdie. We're on Twitter and Instagram at LuxiPod, and our website is luxi.podcastpage.io. Please subscribe and review wherever you listen. This episode, we ask that you find one super fashionable friend and share our podcast with them.